Welcome to this lecture, tubular heat exchangers, and today we will be talking about the shell and tube heat exchangers in details, but before going to that in details, we first of all like to solve that incomplete numerical problem that we have taken up in the last class. So, we will go first to that and if you remember, we have calculated the internal heat transfer coefficient and we have also calculated the external heat transfer coefficient using the appropriate correlations, and we have obtained H I and H 0. So, we have gotten H I as 4911 watt per meter square Kelvin, and we have obtained 1345 watt per meter square as the heat transfer coefficient of the annular space. So, based on this data, we would be able to calculate the overall heat transfer coefficient that is equals to 1 by U is equals to 1 by, this is in terms of the external diameter, and this is d 0 by d I by H I plus this is d 0 and then ln d 0 by d I. So, where we are taking care of the resistance of the wall, and this is the thermal conductivity part of it, and then we have 1 by H 0, this is the heat transfer resistance offered by the external I mean the annular fluid. This is the resistance offered by the fluid the metallic part, and this is the heat transfer offered by the internal fluid flowing through it. So, this is how do we calculate the overall heat transfer surface overall heat transfer coefficient, and then this will come out to be 948 watt per meter square Kelvin. So, once we know this overall heat transfer coefficient, then we would be able to calculate the heat transfer surface area A 0, that will come out to be A 0 is equals to Q already we know, and U 0, and then we have the delta T log mean. So, delta 2 log mean here in this case, if you look at, you will find that delta T 1 is equals to delta T 2, and that is equals to 15 degree centigrade, and so we have both delta T log mean is equals to delta T mean, and it is coming out to be 15 degree. We do not go for the log mean temperature difference, we go for only the mean temperature difference. So, here this comes out to be 15 degree, and from there we would be able to find out the heat transfer area to be Q. What is that Q we have obtained? Q we obtained already MC dot CPC multiplied by delta T, and that we have to put here. Then we have already obtained this 948 and 15, and from there we will be able to calculate the A 0. So, once we calculate the A 0, we will find out what is the heat transfer surface area per unit pin per pin. So, per pin the area of hairpin for each one is 2 pi d 0 into L. So, this is nothing but 2 into pi into 0.0603, and we have the L given as 3.5 meter. So, this will be about 1.325 meter square. So, once we know the A 0 and once already we know the hairpin, so this will be able to calculate it. That will give you the number of hairpin. So, you can try calculating this A 0 from that, and we can then this is already given. So, that will give you the total number of hairpins. So, now with that we will now shift to the next discussion, where we are talking about the shell and tube heat exchangers, and you have already learned about it in the earlier classes. Now, we will try to go in details about this shell and tube heat exchangers. So, we know it is one of the most versatile type of heat exchanger used in the process industries or even in the nuclear plants, and they can be used as preheaters, water heaters, then condenser, and it is used as the kettle boilers, and they can also find applications where including in the geothermal or in the ocean or in many thermal applications, particularly whenever we are using heat exchangers where it needs occasional cleaning. So, that gives us I mean, these are some of the heat exchangers where we typically use the shell and tube type heat exchangers, as I told you, that condenser, steam generators and the feed water heaters. And the advantage of this type of exchangers are that it gives very good design flexibility. We have different type of heat exchangers geometry possible. We will discuss about that part, and the advantage lies not only with the design flexibility, it also gives us pretty good opportunity to use some of the fluid streams where the pressure are very high. And as I told you that the cleaning option is again another big advantage of this particular type of heat exchangers. Whenever we need whenever we are using some dirty fluids and which often generates scales on the heat transfer surfaces, and thereby it gives some kind of fouling resistances to the heat transfer, we have to often clean the exchangers, and that it's not possible for many, it's not possible with many exchangers to regularly clean it, particularly when the hydraulic diameter of the heat exchanger is very small. But in case of shell and tube heat exchangers, it gives that opportunity to clean it at a regular basis. But again, it is so versatile that any kind of heat exchanger design, I mean, we have a guideline given by the Tubular Exchanger Manufacturer Association, that is in short form we call it TEMA, and they tell you exactly what are the standards that are to be followed for design of the heat exchanger. So, we have taken up the heat transfer coefficient for the shell side in some of our earlier classes or in earlier lectures, and there we might have told you how to evaluate the heat transfer coefficient. But as you can understand from the lectures in details of these classes, that is an oversimplification of the actual process, but in reality you will find that the processes are much more complicated. So, we will look into the first of all the design of the heat exchangers, how it looks like. For example, there are different type of shell and tube heat exchangers as we have told, and there are we will only show some of them in this in this lecture. Here you can see this is the cell side fluid. So, the fluid will come like this, then it will be flowing on top of the fluid of the tubes, and then again it will come like this, it will come like this, and then finally it will have a exit from this end. So, here we have the baffles. So, these baffles will allow, or rather not allow, the continuous flow of the fluid along the tube length. So, it will make the flow like following this particular zigzag path or like this, and it will finally come out. On the other hand, we have the cell side fluid or the tube side fluid, which may enter from here, and then what will happen, this will enter over here, this will enter through this space, and then you see we have a divider at this place. So, it is not able to come from here to this point. So, it has to go through the tube side, it will flow like this, then it will take a diversion, and the same thing, this is getting distributed coming over here. At this point they will get diverted and they will follow this path and finally come out of it, and then it will follow this path. So, it is like 1 and then 2 pass for the tube. So, 2 tube passes, that is why we call it 2 tube pass, but this is a single cell pass. So, this is single cell 2 tube pass heat exchanger, and here the another specialty is that of this particular type of exchanger is that this is the tube sheet. This is where we have the tube sheet, and this tube sheet is drilled with the holes to fit in all the tubes, and here finally we get them welded at those corners. So, this will be finally welded, and all these points will be finally welded, and like that we have these parts are getting welded. So, that means these tubes are fixed rigidly with the tube sheet. So, this is the tube sheet, this tube sheet and the tubes are rigidly connected, and that is why this is fixed tube sheet exchanger with 2 tube passes. So, it has obviously gives an advantage in the sense that whenever we remove this part, these 2 ends, if we unbolt this part, and if we unbolt this part, you can understand that these tubes are now exposed, and if we have any kind of scaling formed inside this tube, we would be able to physically clean them. So, that gives the advantage of using this kind of shell and tube type exchanges. So, here we will go to the next particular type of exchanger, where we find that this is a floating head. Now, you see this has become a floating head bundle, removable bundle heat exchanger. So, here in this case what we find is that this is again the shell side tube fluid, there is no problem, it will enter, and depending on the number of these baffles or the type of baffles, it will be diverted and finally come out of it. But what is about the tube side fluid? This is coming over here, they will get and come out of it from here. This is the double pass. So, that is up to that part, but why this complicacy we have in the design of this exchanger. So, now you can understand that there may be situation where the tube side and the shell side fluids are of pretty different temperature, and that may result some kind of thermal stress generation. So, thermal stress will be generated means the cell and the tube, if they are getting elongated at a different rate, then it will generate some kind of thermal stress. So, that means we have to allow the tubes to expand. I mean, if such situations occur, then the tubes will be able to expand as in contrast to the shell side. So, this allows, this particular type of exchanger design allows expansion of the tubes in contrast to the cell. So, they are not rigidly fixed with the tube side, and this is how we how it looks like. Then we have another common type, but this is what we call as the U tube removable bundle. This is one of the simplest geometry that is possible. Say here the cell side fluid, as usual you can see that depending on the baffles, this fluid will be entering here and it will come out from this end. Now, about the tube side fluid, it is simple. It will enter over here, and this is just like that, they will come out and move out of this space. The advantage of this one is that the expansion or differential expansion of the tube, it is automatically taken into account. It is already a U bend, and that if it is differentially expanding, it has the possibility to expand it on this side. Then only one tube seat is good enough to accommodate all the tubes, and if you look into the other fluid stream, you will find that this is coming over there, and then you know it is coming over there, and finally it is moving out like this. But the disadvantage of this particular type of heat exchanger is that if there is any kind of fouling occurring inside the tube, we are not in a position to clean it. So, that is the disadvantage with this particular type of heat exchanger. So, now if we go to the other type, you will find that this the standard shell and type of the front and head types, and the is already specified, as I have told that the Tubular Exchanger Manufacturers Association or TEMA has given so many standards, and that according to that standard we have a different type of front stationary heads, and then we have the rear stationary heads and the shell type. So, as you have seen in the previous slides, that we have one entry side, one exit side or the rear side, and then we have the different type of cell sides. So, these are different, it is as per the specification or the standards. We cannot just like that design any type of cell or choose any type of cell, and they are numbered alphabetically. So, this is an E type of cell, for example. So, if you look at this is E and this is one pass cell, that means this will come here and move out like this. This is a two pass, so it will come like this and it will be coming like this. Here this is the split flow, and that is coming inside, getting distributed and then rejoining and coming out like that. So, Similarly, you have double speed, we have the divided flow, we have the kettle type, and we have the cross flow. So, instead of naming them by individually double speed flow or divided flow, we use these numbers H, J, K, like that, X. These are the type of the shells which are in use. Similarly, as we have seen that we have the channel and removable cover. So, this is for the entry, and you see this is named as A. Similarly, we have other configurations like A, B, C, N, D, and on the side L, M, N, P, like that. We have different type of configurations specified by the TEMA. So, while designing the heat exchangers or using a particular type of, while solving a particular type of exchangers, we have to look for this defined type of nomenclature that has been given by the, suggested by the TEMA. So, now if we look into the different type of baffles, we have several type of baffles that is possible. So, the baffles are basically providing or giving two type of advantages. One is first of all, it gives the mechanical stability to the tubes. That means that if a long tube is there, if a long tube is there and there is no support for that one, there is a possibility that tube will be having sagging at the middle or at the at different points. So, that gives some kind of mechanical support to this, and not only that, it also allows a longer or diverts the fluid from one to the other end, and thereby enhances the heat transfer coefficient, but at the cost of course, the pressure drop. So, as I was telling that there are different type of baffles possible. We have the single segment baffle. So, it is only one segment, then we have the other segment, and if it is, if this is the one corresponding to this, the other one corresponds to that. So, we have about 30 to 35% or percentage of it is cut, and that cut portion is, if it is on this side, the other one in the next immediate successive one will be on the opposite end of it. So, that is how this is the single segmented baffle is used, whereas in case of double segment, as you can understand that we have this part for one end and the other part is at the middle, which is like this. So, this is the one which corresponds to this one, but corresponding to this part and this part, we have this end and this end. So, like that they are arranged in the double segmented baffle. Similarly, we have here the triple segment baffle. So, that means this one, this two, and this two, these three constitute a single unit for the baffle. So, first of all, this is one part, then we have this part, and then we have this part at this end. This will come here, this will come here. So, like that they are arranged in sequence. And then we have other type of baffles also, where this particular baffle is no tube in the window segment. So, that means we have baffles here, and finally, on this part you see there is no baffle in this particular segment. So, this is vacant. So, like this is flowing, and we have on this part again we have no baffle, or no tube in the window segment. This is another type of baffle. Then we have the disc and the donut shape. So, this is the disc and donut shape, this is the disc part and this is the donut, and if you look at the donut part is placed over here and the disc part is placed at the center of the tube. So, this is another type of the baffle. This is called the orifice baffle, where we will find that the tubes are fitted like this. This is a tube and we are connecting, or we have the baffle like we put it the baffle like this. So, if the baffle is like this, what will happen? The fluid will be flowing like it is coming over here and it is passing through this, it is passing through this end. We have, so this is on the cell side fluid, one fluid is obviously going through this as usual, I am sorry, this is this fluid is passing, this is the tube side fluid, this is the cell side fluid, and we have this is the baffle, this is the baffle, and baffle, between the baffle and the tube we have a small gap through which we allow the shell side fluid to pass through. So, that is what is, you see here, this is the, it is forming a kind of orifice at between the baffle and the tube, and that is where the fluid will be passing through. Obviously, you can understand that it will give you a very large kind of heat transfer, heat transfer, but at the same time there would be large amount of pressure drop also. So, now we go to the basic design approach quickly, and we will you have already learned about it to some extent, but as you can understand from the geometry of this particular heat exchanger that any kind of thermal design will be quite complicated if we have to really look into its geometry. So, now here what we do first is the we know the heat exchanger geometry, and in a basic design approach what we first do is we try to calculate or we try to first estimate a kind of design or the heat exchanger, and then we go for the rating. That means, we know first of all we have been given the inlet condition of the fluid, and we know the both the fluid streams, inlet fluid exit temperatures are known. What it is not known is the overall length of the exchanger and other details, how many tubes, how many number of tubes, what is the diameter, what is the cell diameter, etc., etc. So, what we first try to do, we make a rough estimate of the overall length and the heat transfer area. Then we make an estimate of this heat transfer surface area, and then we try to figure out the actual number of the tubes NT, we will the number of tubes we will be trying to find out, and from there when we have some kind of geometry known to us, then we go for the rating problem as if we have finalized the heat exchanger and we have the inlet temperature known to us, and then we try to calculate the exit temperature. So, basically it is a kind of trial and error method, but slightly better than the trial and error. So, if we have the heat transfer known, what is the heat duty that is known, we have the delta T Lm known, because we know in a design problem all the exit temperatures. This F factor generally we assume it to be 0.9 or around, because in a counter current exchanger it is 1, but it is not really a counter current exchanger, and actual value of the F Finally, when we go for the rating problem, we have to get that value, and this u0 now we have to make an estimate. So, we have certain known value, it is already also given in this particular book. One can refer to this book while designing such kind of exchanger, and from there we get the value of u, and from there we can try to estimate the A0. Once we know the A0, we try to find out the number of tubes in terms of the pi d0, and the length is already known. And then for one pass tube, we have, this is the kind of NT, number of tubes, and we have this constants. We will talk about this particular type of constant, why it is coming like this. And finally, we have this relations by which we can try to estimate the number of tubes for different number of passes. And we have this CL equals to 1 for 90 degree, and this is for 45 degree. That is the tube arrangement. This depends on the type of tube arrangements we are following. If it is like this way, they are they are at 90 degree or inline configuration, then it becomes 1, or if it is 45 degree, then this is also 45 degree, corresponding to that CL equals to the, if it is 45, then it is 1. Whereas, for 30 and 60 degree angle, if it is 30 degree, it is 0.87, and if it is 60 degree also, it is CL comes out to be 0.87, and that 0.9 and 0.93 and 0.85, all this tube constant calculation tube count calculation constants that we have used in the earlier relation in the previous slide. If you look at, we have used that relation, and based on that we would be able to calculate the diameter of the shell side. So, we will try to look this one in details in a later on, and finally, you will get, once we have this known to us, then we can go for either of these two types. Either we use the Kern method or we use the Well-Delaware method to calculate the actual heat transfers. So, that is all. Thank you.